how much did you get as this part? How much did you get? I'll write this value and you will know whether you have got this value. Okay, a huge value. 8,46,568.85, something in that manner. And this you will get as 26,52,582. You don't actually require this many digits at all, finally. Okay. Well, I have a certain comment to make here. That is why I have written. Are you all getting something in this area or of this order?
Yes, ma'am.
Okay. Yes, ma'am.
So, okay. So, one point that I want to emphasize here is that, see, this is coming to the reluctance of the iron path is 8,46,000 something. The reluctance of the air gap or air path is 26 lakh something. Remember, the length of the air gap is merely 2 mm, whereas the length of the iron is almost 30 centimeters. Yet, the reluctance offered by this small length of air gap is extremely high because you don't have a mu r in the denominator, or this is extremely high. That is why we are, whereas the iron path is giving comparatively very low reluctance, or it is easily providing a path for the flux. That is the point that I want to make here. See, even though the air gap is only 2 mm of length, it is providing a very tough time for the flux to pass through it because the reluctance is extremely high. So even for transformers, you have not yet been introduced to transformers, etc. But still, I am sure you know what is transformer and all. Basics you have known. Even for transformers, there will be laminations in the core. The core of the transformer is not a solid core. Because of some losses called eddy currents, etc., this core is sliced into many, many parts and then stacked together. And then a bolt is applied. It is bolted together. So in all these cases, they make sure that the air gap, there is absolutely no air gap between these bolts and all these laminations, etc. Because we want the flux, more and more flux to easily pass through that core. We would have preferred a solid core, but because of the presence of some eddy current losses, we are compelled to have certain laminations, or you have to have laminated core. But the problem is that when you have laminated, means small, thin slices, and all these slices are stacked together to form a core. That is how in a transformer you have a core. Now, when they are stacked together, they are made to stack together very close to each other and bolted very close to each other so that no amount of air gap comes in. Even a small air gap of 1 mm or 2 mm or 0.0 mm will become very costly for you because it provides a large reluctance to the path of the air gap. I hope you understood that. I have tried to emphasize and exaggerate more. Did you understand? Someone should answer. Nandagopal, did you understand?
Yes, ma'am.
Yeah. So that is why I have asked you to write the whole value here. Okay. Now the total reluctance will be like something like 3499,151 ampere turns per Weber. That is the unit, ampere turns per Weber. Now I am going to rub off all these portions. Coming to the final part of the answer. Where did I start from? Okay. So what we are going to now find out is this much only. That is, now we have phi is equal to Ni by S. Flux we have as 0.1 into 10 raised to minus 3 is equal to 100. Number of turns is 100. 100 into I divided by this reluctance. Or on solving, you will get I is equal to 3.5 amperes. And you will see that the 34,991, 99151, so much quantity becomes irrelevant because this 0.1 into 10 raised to minus 3 and 100 will take care of all those things. And you will finally get as 3.49, these 3 points only. 3.49, which I approximated to 3.5 amperes. This is the magnetizing current they have asked for. I hope this is clear. So what you do in a series magnetic circuit calculation is essentially you will be finding out the reluctance, total reluctance. How will you find out the total reluctance? Reluctance of one path plus reluctance of the other path plus reluctance of the third path, etc. And when you find out that, I will also say that today we have discussed only an iron ring which is having just a socket. It can be like this also. You know, you can have an iron ring like this, having various dimensions. You can have other various dimensions of the, you know, different parts will be of different dimensions. It can be of different, maybe you can have different, you know, different materials also. And you can have, and also an air gap. So you can have L1, L2, L3, L4, and A1, A2, A3, A4, and also you can have, this will be having some mu r, this will be having another mu r2, mu r1, mu r3, mu r4. In any case, you will be finding out the total reluctance will be S1 plus S2 plus S3 plus S4. If at all you have an air gap here, LG, so LSG. And finally, the total thing is the same. Flux phi is equal to Ni by S. This is S total. This will be given. This will also be given. This is to be found out. Magnetizing current. Or else they may even ask you to find out H, in which case that is another case. But here in each case, L will be different. So anyway, this is the manner in which the calculations have to be done in a series magnetic circuit. Now I am going to introduce, I will do one or two problems on that again, before which I want to introduce you to 3 terms. One is useful flux. Second is leakage flux. And the third is fringing. Now, these 3 points have not been discussed or have not been mentioned in your syllabus, but I feel that you should know this. Only then the study of magnetic circuits will be complete. Okay. Now, suppose I have my core like this. I can draw it as a iron ring, or I can even draw it like this. Okay. For me, this is easier. So I'm trying to draw this like this. Okay. So suppose I am taking a iron path like this and with an air gap here. And I am providing a coil here. Okay. Where I pass current I, having N turns. Now, because I pass a current I through these N turns of wire, I am 100% sure that a flux is formed here. A flux will be formed here. Now, the same flux will form here also. Within the air gap also, the same flux is formed. Let me name that. So, a flux is formed. Now, and the flux in this air gap, the flux formed in the air gap is known as useful flux. The flux in the air gap alone, is known as the useful flux. Why is it called as useful flux? It is called as useful flux because in most of the machines that work on electric flux or a magnetism, as in the case of rotating machinery, which I discussed in yesterday's class, the air gap plays a major role in its working. Whatever flux is available in the air gap is being utilized in many cases. So that is called as a useful flux. Now, you should also remember that the total flux produced, and now we come to leakage flux. What is leakage flux then? Now, we know that air is also a good conductor of flux. So even though we provide a magnetic circuit in the form of a core, air doesn't know there are certain disobedient flux lines there, or air doesn't know there are some tough guys who wants to, who do not want to go along the actual path. So they will go along some path in the air. Okay. They can also, because flux can pass through air also. This path is called as, this flux is called as leakage flux. This is useful flux. So, does the leakage flux do any job for us? No, it does not follow the desired path, nor is it doing any good work for us. The useful flux, on the other hand, does it. So that is it. So because you have two terms coming like this is leakage flux. Okay. So what about the total flux that has been produced by I? The total flux produced by the current I, total flux produced by the MMF Ni will be phi is equal to phi G plus phi L, where this is phi G and this is phi L. I hope you understood. Phi G is the same as the phi in the iron core also. Phi G, I am taking it as phi G because I am right, because I can find out that in terms of useful flux. So the total flux produced by Ni, though I want all of it to be phi G or phi I, some of it is becoming leakage flux. So we come up with something known as leakage coefficient. Leakage coefficient or leakage factor, lambda, is equal to phi by phi G, phi total by phi G, or phi by phi G. Usually it will be greater than 1, or in most electrical rotating machinery, it will be 1.15 to 1.25. This is the normal value of leakage coefficient. Now, one more thing that which remains here, third term that I have to explain to you is fringing. What is fringing? Now, in the air gap, you cannot say the flux will just directly go like this. It has some fringing over there. Goes for fringing also. Because air is also a good conductor. Sorry, not a good conductor, but air is also a conductor of flux. Or air has some permeability for flux. So this portion, this kind of a phenomenon is called fringing. Fringing occurs in the air gap. The longer the air gap, the larger will be the fringing. Now, what is the problem with fringing? Can anyone say? What is it? Whatever we have learned till now is there in that, or based on whatever we have discussed. What can you say? What happens if fringing occurs? What is the significance, or what is that makes fringing a different phenomenon at all? Anyone? Anyone? Can anyone say? Albin Santosh? Any idea, Albin?
No, ma'am.
Alvin, when fringing comes, what happens is, what about the area? Area in the air gap. Usually, in the previous problem, we took this cross-sectional area of the iron as the same as the cross-sectional area of air gap also, isn't it, Alvin?
Yes, ma'am.
Now, in this case, if fringing is there, it means that the area of the air gap has gone higher than that value, isn't it? Because the flux is finding it more, flux is providing, a flux is created over a larger area due to fringing. When air gap area increases, what happens to flux density, Albin? Flux density is equal to flux by area. Okay. What happens for the same flux? What happens to flux density? Albin, flux density goes down.
Decrease.
Understood? So, did you understand?
Yes, ma'am.
Albin. So, I hope all of you understood. So, because of fringing, what happens is that the flux density inside the air, inside the iron core, and the flux density, flux is the same, okay? Flux is the same. But flux density inside the iron core and flux density in the air gap are different. Air gap flux density will be lesser because area has gone higher due to fringing. Now, what if flux density goes down? What is the problem? Is there any problem? Sometimes. No, now go back to your BH curve. Okay. When you draw the BH curve, remember it had a saturation point, saturation area, this area saturation, which means even if H is increased, B doesn't increase, it is straight. It doesn't increase, it's saturation area. Saturation. So if in circuits where you need to reduce, saturation means, all of you should understand, this portion is the portion where you have a linear part and we are all happy to work in the linear part. The moment it goes to this part, the saturation part, it becomes non-linear. Non-linear means the cause and effect are not linear. Whatever you give, the output may not be the predicted one. ഞാൻ ഒരു അടി അടിച്ചാൽ ഒരാൾക്കറിയാം, മറ്റൊരു അടി അടിച്ചാൽ മറ്റൊരാൾക്കറിയാം. രണ്ട് സൂപ്പർ പൊസിഷൻ പ്രിൻസിപ്പിൾ, രണ്ട് അടിയും കൂടെ അടിച്ചാൽ മറ്റുള്ള ആദ്യം അടിച്ച അടിയുടെ കരച്ചിൽ അടുത്ത കരച്ചിലുമായിട്ട് കരയണം. Or superposition principle is not applicable. Let me not go wild into all those things. Okay, saturation is the part where you have non-linearity coming in. Working with or analyzing that part is difficult. So all our machines, all our electrical machines are designed so that the flux remains in the linear part, or the flux density is in the linear part. Or if at all a saturation comes in, it is difficult for us. So what we can, an air gap can be deliberately included in a magnetic circuit, if at all needed, so as to bring in fringing and thereby increasing the area and thereby decreasing the flux density, so that the magnetic circuit or the flux doesn't go to the, flux density doesn't go to the saturation area, or the core doesn't get saturated. Or the magnetic, okay.
Ma'am, area കൂടുമ്പോൾ reluctance കുറയില്ലേ?
Area കൂടുമ്പോൾ
reluctance
കുറഞ്ഞാലും, what about the air? The air in the reluctance is extremely high. Okay. Air in the reluctance is extremely high. And what about the length also? Air in the order by which flux density decreases cannot be, compared with the reluctance decrease in reluctance. Okay.
So flux remains a constant.
Flux remains a constant. Flux in the order, that is the difference. Flux remains a constant. Flux is a constant so long as this current and number of n is the same. Flux cannot change. Leakage flux, ബാക്കിയുള്ള എല്ലാ ഫ്ലക്സും എപ്പോഴും ഇതുണ്ട്. So that is the main difference between electric current and electric circuit and magnetic circuit. See, resistance remains the same there. And consumption of energy. Even you are just maintaining it, or the energy is just to create it. Then it remains there. Flux is the same. Always you have to remember, flux when it is produced by MMF. Okay, flux is the same. Flux density varies with air gap or with area. That is what is happening in all the electrical machines also. And we want the core not to go to saturation. Okay. I don't know if I have gone haywire. Lots of things have been injected. So did you understand these 3 points? Useful flux in the air gap, leakage flux, where it forms new paths within the air, which is not useful for us. And then because leakage flux occurs, the total MMF used to produce. So what happens is that if I want 1 Tesla of flux density here, or if I want, say, 5 Weber of flux here, if 1 Weber is lost in as leakage flux, I may have to push more current. Usually, if there was not leakage flux, say I had, these are just small layman values, okay. I had just, say, 10 amperes to pass through 100 turns. 100 turns passing, 10 amperes passing through 100 turns would have produced 5 Webers if there was no leakage flux of 1 Weber. But if I want, but I know that 1 Weber is lost as leakage flux, and I, at the same time, I want to maintain the flux in the core as 5 Weber itself, then what will I do? I increase the MMF. Either by increasing the number of turns, or by increasing the current, so that I can maintain 5 Webers itself here. I increase the MMF, so that even if the leakage flux is there, I can maintain the same flux. This is the overall. I hope this much is clear. The time we'll be continuing with, we'll be continuing with magnetic circuits in the next class also. You can have a break. I don't know if I've given you lots to think about. Have I? 2 periods together?